Hi, everybody. This lecture will cover Chapter 1 of the textbook for electric circuit analysis, the 12th edition of Nilsson and Rydell, Chapter 1, and the title of this chapter is Circuit Variables. So as we begin through this chapter, there are a couple of things that I just want you to know. Before we get started, today I'm going to do the lecture that will cover all of the material that's necessary for you to do the homework for Chapter 1. But there are a couple of things that I want you to make a note of. And the first is here on our Moodle page, you can see what our schedule is so that you'll know when we are going to be doing what topics. But the other thing, I've posted a few items on our Moodle page that I think are extraordinarily important. So important, in fact, that you should consider committing them to memory. And when we have exams and so forth, I'm not going to require that you have these things memorized, but basically the international system of units that govern electricity, derived units, in other words, this gives you a working knowledge of how they fit together. And then I have another formula here that shows you the important formulas for Chapter 1. And once again, these are things that I'm not sure that you're going to need to commit them to memory 100%, but they're going to govern your work as we go through this material. The other piece of advice I want to give you when we start working problems, the units given here are base units. So volts, joules, coulombs, and so forth. I would recommend strongly that you always convert to base units. So in other words, if a value is given to you in milliamps or a time is given to you in microseconds, don't put those into any of the governing formulas in that form. Always convert them into volts, joules, seconds. And then when you come out with the final answer, you can make a determination as to what the proper unit would be with the SI prefix. But this is just something to keep in mind, because otherwise the formulas, electricity was sort of dealt with for the first time before, or I apologize, after the metric system was widely used. So there's a lot of units in electricity that are very, very consistent, but you can still get into trouble with the units. So having said that, let's move forward. The first thing is we're going to have an overview of circuit theory and sort of a recipe for solving circuit problems, which is more promising than it sounds, more promising than it really is. And then we'll talk about these tables that I've posted up to the web page, to our Moodle page, just because they're so valuable. So having said all of that, how does circuit theory fit into the overall scheme of things? Well, this slide shows you a little bit about how circuits, how engineering design in general works. And you'll notice that the first step is a need, and then second is a design specification. So the difference between an applied science like engineering and a pure science like physics is engineers are always building to some sort of an outcome. We have a problem that needs to be solved. We have certain constraints put on how we can solve that problem. And then we start with the physical concept and work our way down from there. So this diagram just sort of brings that into a schematic that you can take a look at and see kind of what we're talking about. But we always start with what we need. So because we're always rooted in the real world, it's also extraordinarily important that you do a couple of things very, very well. One is to always understand that your units are as important as your number in the answer. And the other is to report things in the proper number of significant figures. So if you're given something with 2 significant figures and multiplying it by something with 3 significant figures, there's absolutely no way that your answer has any meaning at the 5th significant figure. So you apply those rules, stick to basics, and make sure that you have your answers written that way. Another important thing, we have some definitions here, which I think are very important. Voltage is measured in volts. The best definition of voltage I have ever heard that makes it very simple for me is that voltage is the separation of charge. So and that I guess I have to introduce the idea of amperage as well. Current is the movement of charge. So electrons hold a charge, which is negative, but we'll probably deal with it in this other way where we don't look at it as being a negative charge. But electrons carry a certain charge, and that charge is given in units of coulombs. If you take those electrons and you separate them across some sort of a barrier, you have a battery, and that creates a voltage. If you have them moving, you have the movement of electrons through a circuit, or through an appliance, which indicates a current. So current is the movement of electrons, current is the movement of a charge, and voltage is the separation of a charge. So having said that, what are we trying to do? There are several different things, and your author breaks down 4 big major types of electrical devices that we may design. But one of the things that we often try to do is to generate power or to move energy. So once again, we have to be very careful with our variables and our definitions. Energy is an amount measured in joules. Power is a rate measured in joules per second, which has its own unit of a watt. So a kilowatt, for example, is 1,000 watts or 1,000 joules per second, meaning that is the rate at which energy is delivered. It's not an amount of energy. So this first defining equation, V is equal to dW over dQ, says that voltage is equal to the differential of energy divided by the differential of charge. Or that energy per unit charge is a voltage. And I'm still kind of avoiding the sign convention for right now. Current is defined as dq dt, where the current amperage is equal to charge over time. So that gets back to that idea of the movement of a charge. Okay, so the other thing to keep in mind here, I is the variable that's assigned to current, and the unit is amperage, which is capital A. Q is measured in coulombs, which is assigned the capital letter C, and time is in seconds, which is a small s. Voltage, which is assigned the variable letter V, is measured in volts, which is a capital V. W is the unit of energy, is the variable of energy, which is measured in units of joules. And once again, Q is measured in coulombs and represents electrical charge. Okay, so first of all, let's talk about a circuit. In everyday life, we might talk about like anything as being a circuit. So you have a battery and you light a lamp with it, and that's a circuit. In this class, and technically speaking, a circuit is not an appliance in the real world. A circuit is a mathematical model of something that would do one of these electrical functions. And by the way, electricity is the study of all of this stuff. The basic unit, or the basic small division, or the thing we're most interested in when we study electricity, is charge. And charge is measured in coulombs, right? So when we talk about amperage, when we talk about current, amperage is another name for current, but current is accurate. So we talk about current, we talk about voltage, we talk about coulombs, we're talking about elements of the science of electricity. When we're talking about a circuit, we're talking about a mathematical model that represents something probably in the real world, but we're not talking about a real world thing. So here we have an ideal basic circuit. Ideal means that it can be described solely in terms of the relationship between voltage and current. Basic means it cannot be subdivided into simpler. And as I said, a circuit element, we're talking about a mathematical model, but we're talking about only two terminals, basically where current goes in, where current goes out, carried by a voltage. So it's ideal because we have a description, or we can describe it in terms of current and voltage. And it's basic because it can't be subdivided. If we take away any of those elements, we really don't have a circuit at all. And we just have two terminals. And this is how we form an ideal basic circuit. All right, so we have a few of those definitions that we've talked about. And here, hang on a second. Okay, and here we have the equation for power. So power, which I said is measured in watts, is basically the rate of energy per time, or dW dt. Power, which is a joule per second, power, which is energy per time, is a watt, which is a joule per second. So all of these are kind of the way that these things interact with each other. All right, so if you put all of these together and you realize that power is dW dt, dW over dq times dq over dt is equal to V times I. So power is equal to voltage times current. This is an extraordinarily important equation when we are talking about electricity. So all of these equations, I'm going to take a look here at when we have chapter 1 right here, and we're talking about circuit variables. I'm going to skip out for just a minute because I want to show you something on our Moodle page. Which is listed under important variable or important equations. So I've written out the important equations here. You see V is equal to dW over dQ, I is equal to dQ over dt, power P is equal to dW over dt, and P is equal to VI. Then above I have the important variables, and the unit that they're measured in, and the letter abbreviation for those variables. So all of that is listed in that element on your Moodle page. So you can refer to this as you're working through the problems. Righty, hang on just a second. Find that again. All right. All right, so here we go. The next thing we need to talk about is this sign convention. Now, the first thing to recognize is that the sign convention is completely arbitrary, but having said that, you need to use one sign convention and stick to it unrelentingly. You must be relentless in your application of the sign convention, because from that sign convention, everything else flows. Is a circuit absorbing power, or is it releasing power? These are the sort of things that you need to know based on sign conventions. You have to be consistent. The sign convention that is most often used is referred to as the passive sign convention, and this is the one that we will be using in this class, and that I will work toward making sure that you're familiar with. But the passive sign convention is based on this idea. Whenever the reference direction for the current, for the current in an element is in the direction of a reference voltage drop, so high to low across the element, we use a positive sign in any expression that relates the voltage to the current. Otherwise, use a negative sign. So let's take a look at this, the practical use of a practical sign convention. Here we have a positive voltage and a negative voltage, right? So we're going from positive to negative. the current is moving this way. So that means that the power is positive because the current and the voltage, the current is in the direction of the voltage drop. On this next slide, we have a couple of different ways to express it. Here, the power is negative because if you look, the positive terminals over here, the negative terminals here. So that means that the current is flowing opposite the voltage drop. Same here, it's flowing in the opposite direction. And here we have a positive because it's flowing from the positive to the negative. Okay, so what is the meaning of positive power and negative power? When you use this sign convention, the power associated with the circuit element is negative, means that the circuit element is generating or delivering power. When the power associated with the circuit element is positive, it means that it is absorbing or dissipating power. So when you look at this chart right here, it goes along with this definition. Otherwise, everything will be backward from that. Okay, so let's take a look here. What's going on here? We have current. This would be a positive current and a negative voltage. So that's negative power. That means it's supplied. Same thing here. We have a negative amperage and a positive voltage, negative current, positive, and so that's supplied. Here we have a positive current and a positive voltage, so it's absorbed. So it goes along with this idea. Positive is absorbed, negative is supplied. So you can see that this is, I mean, you can do it the other way, and actually some organizations in some countries do it the opposite way. You just have to do it the same way every single time. Okay, so here's an example problem talking about finding the total charge entering terminal 1. So we start with this basic equation, I is equal to dq dt, q is equal to this function. We integrate, right? Separate this, integrate it, and we come up with 4,000 microcoulombs. It's asking for a charge. Charge is in coulombs. It's a tiny wee little coulomb, so we write it in this way. Now, the other thing I want to point out is each one of these answers has one significant digit. Okay, it would not be correct to write this as 4,000.000. Okay, it has one significant digit because the number going into it, the current, has one significant digit. Okay, and there it just tells you what the correct answers would be. But once again, always with the one significant digit. All right, assessment problem number 1.5 is described here. Once again, we have current going into the negative terminal. So what does that tell you? This is a negative, so we have power generated. Here, we have amperage coming out of the negative terminal, so it's in the positive direction. So this is 80 absorbed. The other way you can think about this, it's not as clear, but if you start to become confused and think about, we have voltage, the voltage is the same in both of these, right? But the current is coming out of the circuit here, and the current is going into the circuit here. All right, here's another example where we have find the total energy delivered. Energy, once again, is in joules, so we want to find that variable for W, which will be measured in joules. Okay. Now, like I said, this is on your Moodle page, so you can look at this at your own pace. Now, one other interesting thing, if you think about it, if you have a circuit, the power associated with each circuit element in a legitimate circuit, if you add all the power that is absorbed together and all of the power that is supplied, that answer has to be 0. So that is actually an excellent way to check to make sure that your circuit calculations have integrity. So if you calculate, you have a voltage and a current on each one of these elements. They're given below, right? So in each case, you can compute. First of all, you can get the sign, you can get the amounts, calculate the power, whether it's positive or negative, and then the total is going to be 0. If there's an example in your textbook where the answer is not 0, and when you look at that, it's because there's a flaw in the way that the problem was created. It's done on purpose because they want you to see how to use power as a check in a circuit. All right, so the last slide here, as it says, the power in a circuit always balances. This means that the total power supplied equals the total power dissipated. So there's no net power generation or dissipation in a circuit. This is a great way to check your work. All right. So that is it. That's the extended lecture for chapter 1. Some of the things that I hope you'll come away from this with is that there are some very good resources on your Moodle page for you to check. I also worked a couple of the other assessment problems right down here, so you can see how those work out. Make sure that you're familiar with the SI units. We've talked about all of the base units here. We haven't really talked about luminous intensity or amounts of substance, but we talked about current, time, and those are mechanical units more often. Then we've talked about energy in joules, power in watts, electrical charge in coulombs, electrical potential in volts. We've not yet talked about resistance or conductance, or capacitance, or flux, or inductance, which we have in labs that we've done in physics, but those are yet to come. So I've not posted the homework problems yet for chapter 1, but they'll be posted by the first day of class. So everything will be up and ready for you. And having said that, I will see you in our first lab day. If you have any questions, please have a start, and I'll answer your questions at that time. Or if you want to get a hold of me beforehand or after, you're also welcome to do that. The other thing I do want to point out is each time we have a lab, you'll have a pre-lab, which involves reading the lab. So we'll do a lecture and a lab kind of at the same time. We're only doing 3 lab procedures before spring break. So your job before we come to lab on January 15th is to read the pre-lab and to submit the pre-lab questions. There's just a couple of them, but read the lab procedure, and we'll talk about I'm so sorry. That is actually that's actually going to be for our second lab period. For our first lab period, we have lab safety and procedure expectations. So I'd like you to read the document at the top of your Moodle page. That looks like this. If you pull up lab safety and procedure expectations, then on the next lab day, which will be the 22nd, is where we'll go to lab procedure number 1, and you'll read the pre-lab and lab procedure, and then submit the pre-lab questions. All right, everybody, thank you for your attention. I'll look forward to seeing you on the 15th, and please do not hesitate to reach out if you have any questions or problems before then. Have a great day.